Hello and welcome back. So in the last class we discussed about DC motors. DC motors, different drivers that can make it run. So one of the demonstration that you saw, we used an industrial controller and industrial drive through which I communicated to the drive using EtherCAT, and finally I attached a DC motor, standard DC motor without any encoder or anything, and I made it run. Okay, so that is one of the approach of running DC motor using industrial controllers, and the theories we have discussed already in our last class. So continuing that in the same sense, so today we will be discussing about stepper motor, which is one of the very broad class of actuators which are commonly used in robotics since long time. So here is the outline. Here is the outline for my today's lecture. So I'll be introducing you to stepper motor with working of unipolar motor and bipolar stepper motors in detail I'll be discussing. I'll also be discussing something on micro stepping, hybrid motors, variable reluctance stepper motors, and I'll show you a demonstration when I have used a standard stepper motor, industrial stepper motor, and I drove it using industrial servo motor drive. So here we begin. So starting with the stepper motor now. So yes, so what exactly is an stepper motor? Stepper motors are small DC motors. Normally they were small. Nowadays it is not that small though. So yes, you must have seen your digital watches. So what you have seen is at every second it moves by just one tick. Okay, 1 second, okay, 1/68th of a 360-degree angle that it can make. So what you have seen there is they were also a specialized dedicated low powered stepper motor which can move just in 1 second, one small displacement it used to do. So yes, even stepper motors are very similar. They are electrical devices, electrical motors which can move incrementally in steps in response to some programmed input pulse trained to its wires. It has 4 wires or 5 wires depending on the type of stepper motor it is. So all the wires will carry some sort of electrical pulses, and the pulses, the level of the pulses will be as high as the driving voltage of the motor itself. Okay, and the different pulse order will have a different positional places in the circular dial of your stepper motor. So changing the order of the pulse basically changes the direction of the rotation. Okay, so order is there. So we'll see when we'll actually discuss stepper motors. Okay, so they are digitally controlled and they do not require any digital to analog conversion to do position control. Like in case of a DC motor, if at all you want to do position control, you have to take feedback in terms of angle is to be converted, it is to be compared, and then you have a controller which compares and does some sort of control. So that is all not there in case of stepper motor. Even if you want to do precise position control, the hardware allows you to do even without any feedback. Okay, so as long as I must add on to this, as long as the load is within the prescribed limits and the motor is not slipping. Okay, so these motors are widely used in open loop controlled applications where the load is predefined and you do not require any feedback system, and the control circuitry in this case is a little complex as compared to DC motor. Still they are inexpensive because you are able to do position control even without a feedback. So feedback mechanism is totally missing, and that is what is making it still inexpensive. Okay, so it has a holding torque as long as it is powered. Okay, it can stand still in its place. Okay, and it has its own holding torque. So any external torque will not deviate it from the position where it is locked now. Okay, but yes, while running it can offer some jerks because it moves incrementally like a clock. So every next location where it goes, so there is a jerk in between. Okay, so it goes, stops, like that. Okay, So yes, the application what you have seen is a small dedicated digital watches. There are other very common that you might not have noticed at time. That is your standard printer. Standard printer has got a paper roll that uses this type of motor. Even the cartridge moves using this type of motor. Similar machines are fax machines, scanners, copiers. All those they use small stepper motors. Small robotic arms, CNC machines. 3D printers, you have already seen 3D printers have got 3 stepper motors which are orthogonal to each other. Each of them are moving your head to each different location. Okay, so imaginary devices, printing press, textile machines, gaming machines and robots also. So they all use stepper motors. Okay, but they are all, I tell you, they are all small stepper motors. Industrial stepper motors can be very, very big as compared to them. So different types of stepper motors are permanent magnet, unipolar, bipolar stepper motor that we'll be discussing today. Variable reluctance stepper motor is there. Hybrid synchronous stepper motor is there. They are commonly used in the industry. We'll discuss a bit of that also. So yes, unipolar stepper motor is one of the types of stepper motor. Let us discuss this. So this is one of the simplest of its kind and it is most economical type of stepper motor, and it has 5 or 6 number of wires. 1 or 2 which is here are the common ones. They are the common ones. If you can see my cursor, yes, it is this one and this one. So all together it is different motors that you see started running. I should stop this one before we discuss. Okay, so yes, so these are different 4 wires, A bar, B bar. Basically if A is high, A bar is low, B is high, B bar is low. So 4 different wires will have different signals which are like this, and A common and B common are the wires which are connected together to the ground. So they can be either connected within the motor itself or outside the motor they can be done. In that case it is 6 wire if it is outside. Okay. So yes, it has 30% less torque as compared to bipolar stepper motor. We will be discussing bipolar stepper motor as well later on. Before to that, let us discuss this one. And then operating modes, they can run in half step, full step, micro stepping. We'll see all of these. Before we go there, let us first see this one. So if you remember, you can do switching using transistor. Let us say this is your high line where you have voltage of, let's say, 24 volt. If your motor is 24 volt, this is your transistor. This is where you must be having some sort of resistance everywhere, small to bias the transistor, and this is your input. Okay, so your motor can be fitted somewhere over here. So when you give it a high signal from here, this current from here that comes and finally that drives this motor. So this is a way you can switch using transistor. If it is, this one is for NP and transistor, it can be even for PNP, a different connection can be made. So yes, this is a type of switching that you did using a standard transistor. It can also be done using MOSFET. Okay. So yes, over here in our circuit also, if you can notice, so you have all these similar connection. You have all this similar connection. So A can be switched by this wire terminal which is here. A bar has got another terminal that goes here. So what is the difference between A and A bar? I tell you. So if current flows from A, okay, it comes like this, it comes like this, it is wound on one of the wire pole and it goes and it is reverse wound on the other pole, so that when A is high, it makes the bottom one north and upper one south. Okay, and finally it goes to the earth. Okay, that is to the ground. And A bar is high, in that case wire comes from the other side of it and it is making the upper one north and the bottom one south if it is. So it goes back to the ground once again. Okay, so this is to make reverse the polarity of the pole which is there. So So north becomes south, south becomes north from one pair of the set, that is A and A bar. So similar is the connection for B and B bar, that is controlling the horizontal pole which is shown here. So that will control the current over here in clockwise and counterclockwise direction finally, and will make the polarity reversal in these two poles. Okay, so you have four different poles, two pair of two. So yes, now let us see how it works. So let us say your motor has started already. Okay, it is here in this position. What you see, the blue one, if I say, is the south pole. Blue one is the south pole which is attracting the north pole of the armature. Armature is at an angle now. So yes, so when both the poles are high, armature goes to this particular position. This is a magnet which gets attracted towards the pole which is high. Okay, in the next position you will see, so one of the pole is only high, other one becomes opposite to that. So next pair A bar is now off. So both the wires which are here are 0. Okay, both the wires which are here are 0. So in that case what will happen? So you have just B which is high. Okay, as over here in the truth table also you can see. So initially it was in this position. So you see both of them are high. A and B both are high. Armature was like this. In next position, when you have only B high, only B from here, this transistor is switched on, it goes to this location. Okay, so what happens in that case? This is the north, this is south pole, blue one, and this is the north pole, right? And armature goes like this. And next position, when you have B and A bar high, okay, that is the position which is here. This is B and this is A bar which is high. So again the bottom right corner is now your polarity which is south. So ultimately this armature, it comes like this. Okay, and next consecutive pulse phase will be only A bar is 1. In that case it goes to, okay. So yes, only when this is high, A bar is high, it has come here. Okay, A bar is high, it has come here. Okay, and in the next phase, so yes, now it is A bar, B bar both are high. In that case you see the armature is like this, and then next is this, when only B bar is high, again next one will be B bar and A is high. So it goes back to this position when it is B bar and A is high, it comes here, and then it goes back to the original location, that is when only A is high. It is the last stage. So in total 8 steps it made one full revolution. So you see how it works. By the time it keeps running, we can discuss other things. So this type of running, when you have number of poles and the armature is able to go even to the midway in between, so that is because of energizing of both the poles simultaneously. So that is half step running. So one full step is pole to pole. So half step is pole, half pole, pole, half pole, pole, half pole, like that. So it will rotate like this. Okay, so that is what is half step running. Okay, so and apart from this, your robot can, your motor can also run like this. Let me just show you this way. So yes, what you can do here, so you have a pole which is somewhere over here and there is a pole which is here. Okay, so you can gradually shift the power from this. If this is north, so this can be made north as well, but you gradually shift the power from here to here by controlling the current. In that case your armature goes from here, this position, to finally this position by gradually changing its position from north to south. So that is a way we can run using micro stepping technique that we'll discuss very much in detail later. Okay, So yes, so that is a way. So yes, this is how your stepper motor keeps running and running. So every pulse set to all the 4 wires, you see your armature is at a particular position, and then next pulse sequence, then it is at a different position, and so on, so forth. So you see every pole has got double winding. One is clockwise to make it north, another one, if it is A bar, which is counterclockwise, which is making it south pole when it is faced to the armature. Okay, so north and south. So one of them is always a dummy coil. So for the same motor, you have 50% of the coil at least which is not working all the time. Okay, at least. Okay, so that makes it 30% less torque as compared to bipolar stepper motor. Okay, now let us see what are other types of stepper motor also. So commonly used driver is ULN 2003 or 2803 that uses 7 or 8 Darlington transistor arrays. So I should again discuss this one. So let me come back to this whiteboard. So yes, yes. So what is a Darlington array? It is, I think, nothing but something like this. So you have a transistor, okay, with which is in switching mode. It comes here, and then you have another transistor that goes to the ground. Okay, so what happens when this is high? Okay, it makes this 0. Sorry, this also is high. This further biases the other one, and finally you see if you connect any motor here, that is switched on. Okay, so high on can make high over here. So ultimately the high current, this can control a high amount of current as compared to a standard small transistor set. So that is the reason this is used. Okay, so yes, this is how a simple unipolar transistor stepper motor is run. Okay, now let us see what is a bipolar stepper motor. Before moving on to that, let us just discuss how we controlled the polarity of a coil using a standard H-bridge driver. So you had 4 switches, you remember, S1, S2, S3 and S4. If you switch on S1 and S4, your current enters from left to right direction in the coil, whereas if you switch on S3 and S2, the diagonally opposite one, your current flows from right to left. So that is to change the direction of flow in the coil, you use this. So similar is the case when you can use 4 transistorized switches or MOSFET switches to convert the direction that is flowing to the coil, reverse the direction of current which is flowing through the coil. This will make it north or south pole, reverse polarity one. So this is something which are going to use in this case. So now a single coil is not energized, same coil is made north or south depending on the direction of current. So now you come here, now you will see, yes, each one, if you can follow me. So this is a H bridge. So this is one H bridge which is called A1, this is B. So A set has got AH and AL. So if AH and AL bar is high, current flows from here, this makes it a north pole, red one is the north pole, and same wire goes here, wound in reverse way, and finally it goes back to the S bridge. So this makes this one south pole. So flowing current from here and finally like this will make it north and south, whereas if you switch on A bar over here, so diagonally opposite switches are switched on, in that case what will happen? So you have current that flows in a reverse manner and makes the poles reverse. Okay, same happens to the B and B bar poles. Okay, so they are also a pole, to pair of pole which are north and south with the same winding flowing through them, same winding that flows through them. Okay, so how is it? Let me just draw a little more in detail over here. So if you have a magnet which is here, you have another magnet which is here. So you have a single coil which goes like this. It comes here, it is wound in a reverse manner and it is coming back. So current flows from here, it goes like this. if this makes this north, this is south. So what will happen if you make your current go like this, okay, go like this, it comes like this, there is no double winding, mind it. So yes, same wire carrying opposite current. So in this case, this will become north, this will become south. Got it? So this is how it is wound. Okay. So yes. So now you see what miracle you can do with the same pole without any duplicate wires. So without any duplicate winding, now you can see you can make it run like this. So you see now top right corner is both of them are south, bottom left one is both of them red in color, they are north. So you see what happens. So one by one you can switch off also. So this time I have switched this one off. Okay, the A bank is totally off, B is on. So armature came here. So B is on. Okay, then comes here when you have B bar and A is on. This is the another state of this motor. Okay, and then only A bar is on. Again next B bar, A bar, okay, then B bar A, and back to A. Okay, so this is how you can convert, you can make it go like this. So you can keep moving like this. You can watch one full cycle carefully. This is how it works. So this is again having very smaller in size as compared to similar power to weight ratio of a unipolar motor. Okay, so it has very high power to weight ratio as compared to a similar sized unipolar motor. Okay, so this is the truth table for this. Let me pause this one, so show you the truth table. Yes, it goes like this. First one, when AH BH is on, then you have BH, then you have BH AL, next AL BL, AL only, and then AL BL, BL, BL AH, and then only AH. So this is how this also can keep moving. Okay, so this is how it can keep continuing. And if you reverse the direction, so how to do reversal? You just do something very reverse. So it rotates in counterclockwise manner. So doing this can make it go this way. Okay, so doing this will make it go in opposite manner. Okay, so same here. So if it is moving like this, so you just have to reverse the sequence of the pulse that goes to the coil. So that way you can reverse the direction. So you can precisely control the position, you can precisely control the direction, okay, and easily control the direction, and you can control the velocity. So if you go very fast like this, right, very fast, so this motor can go very fast. So higher is the pulse per second, pulse sequence changes per second, higher is the speed. So speed can be controlled, position is automatically controlled, right, and direction is controlled by changing the pulse sequence also. Okay, so this is how it works. Okay, so this motor has just 4 wires and 2 reversal phases, right, and less winding, so it saves space and cost. It can also run in half step, full step, or micro stepping. So you can just leave the single pole steps. This one you escape, you directly make it high. Okay, so this one is skipped, this one is there. So in 4 steps, 4 pole pairs are covered. That means it is full step. And micro stepping, if you can gradually shift power of the electromagnets, that is the poles, from one to the other, if you can gradually shift, your armature can move in very gradual manner. Okay, so yes, the possible drivers for this is L293 and 298. That is a dual full H bridge driver, which you know, that is through your embedded knowledge maybe, or hobby electronics people do it. There are industrial drivers also for this. Okay, so now let us move to the modern stepper motors and driver. We'll also see a demonstration for this. Okay. So I've been talking about micro stepping, even for unipolar, for bipolar, how it is actually done. Okay, so just see this carefully. This is exactly same. This is your bipolar stepper motor. Now what we do here is we gradually shift the load. So how we do it? So you have to switch the power from one of the poles to the other pole gradually. That means this time you don't have to make a coil high or low. Okay, high shifts from one of the pole to the other one, it gradually shifts. Now you have to control the current. So you know strength of a pole depends on the current that flows through it. So it requires a special type of drives which are known as current chopper drive, which will gradually shift the field. So how it can shift the field? Because one of the pole is high, this one gradually dies off, other one which is there, so this one gradually picks up. Okay, so you have two poles, so your effectively energy is transferred from one of the pole to the other one. Okay, so it uses a DAC, digital to analog converter, that it is there. So the higher is the resolution of digital to analog converter, so higher is the current control you can obtain from 0 to maximum. If it is a 3-bit, so maximum could be 0 to 2 to the power 1 to 2 to the power 3, that is 8 intermediate steps of current control you can. So yes, it reduces the step size and also reduces the resonant behavior of your motor. So they are less noisy in that case. Okay, they are quieter. Continuous motion can be achieved with extremely low speed is possible. Okay, they are creating less noise also. The most effective stepper motor with slightly higher cost because it includes a bit more of electronics here. Okay, so this is the step operation. Now you see when A is high, it is high for quite long time. Okay, quite long time, you see. So it is high. Okay, you are making it high but not allowing full current to flow using the chopper drive, which is actually powering the H bridge in total. So yes, what will happen? So gradually you see it goes from here to here. So you can see a complete detail in this link if you can follow, which is here. Okay, so I'll share this link detail in the resources section. So don't worry, you can directly go there and you can read further. There are a pretty good amount of stepper motor videos are there on YouTube. I'll share a few of them to you all. Okay, so what it is doing, basically if at all you want to switch, now let me go to my whiteboard once again. So yes, so now what is happening here, so let us say you have two pole, you want to shift your field from here to field here. So what effectively, let us say resultant field is somewhere over here. So this is what you want to rotate. So this is the resultant field. So that is √2 times of these fields. So if it is at 45 degree, let us say if it is at just theta. So what is there? So it is FR cos theta and FR sin theta. Right. So what effectively should go here is FR is the full resultant that you can get, that is √2 times of F. Okay, so F varies. Okay, so what happens? So one of them, if you keep on increasing theta like this, so the pole will gradually, so FR cos theta over here, when it is 0 degree, this will be the maximum one, this will be the maximum one. If it is minimum, that is at 90 degree, what will happen? This will completely die and this will become the maximum one. Okay, so this is the way it gradually goes from here. So at 45 degree, the position which is shown here in this figure, so if you can see this, so at 45 degree, it is F cos theta, both sin theta both are equal, that is 45 degree, that is 0.707. So by percentage wise, if you see, it should be 0.71% approximately. So 71% of pole strength will effectively create the full strength at the 45 degree location. So this is the position here. So that is one of the demonstrations. So yes, it varies. In one of them it varies as cosine, other one it varies as sine A. Yes, and that is how it works. Okay, so yes, you have a chopper drive that can do micro stepping also. Okay, so these are some of the commercially available stepper motor drivers for small robots and devices. This is a commercially available one which you can club through different embedded systems, microcontrollers, because it has 5 volt current, 5 volt signal which is required to signal it, right, to change the direction, to move every pulse of it. So this is a dedicated chip which has all the driver circuitry which is required to run a bipolar stepper motor, whereas the right one is an industrially safe one to some extent. Yes, that has the capability to do micro stepping driver also. Okay, so it has some configuration switches which are here. It has some configuration switches which you can see here. Okay, and then you have enabling switch, enabling, that enables a motor. So it has A bar, B bar, those wires which can be connected here. It is sometimes these type of drivers has Modbus connection already to address the stepper motor velocity and address the stepper motor pulse signal. You can do everything from here, or you can directly control it using the direction bit. So you don't have to take care of 4 wires, you just have to address the pulse bit, which will one high pulse for one tick. Okay, one position shift, one another high pulse, another shift, one high pulse, another shift. So pulse rate will determine the velocity. Okay, and every pulse will remove it by another incremental one displacement. So this is a type of driver which is there. So we'll be using even higher up in the industrial sense. So this time I'll be using a Beckhoff EL7031 series one, which has one channel stepper motor motion interface. Okay, it can handle almost around 24 volt stepper motor. Okay, and 2.8 ampere of power contacts without any encoder. It cannot see even stepper motor, although it can run in open loop. Sometimes they are also fitted with a, to ensure that yes, it has reached there, it hasn't handled any over torque at any point of its motion. So you may have a feedback to be doubly sure, right? So even steppers are servoed sometimes. So this has capability to run it in step mode, that is full step, half step, or 64-fold micro stepping. So what does it mean 64? That means one pole to other one, it can shift in 64 bit, 64 fold. So how many bits actually it is? You can imagine 64 intermediate positions. So that means 2 to the power 6 intermediate steps at least it can go in between. So that is a micro stepping it can attain. Okay, current control frequency is very high, that is 25 kilohertz. So what happens? So 25 kilohertz means it has a very high change in current which you can see. So in that case it doesn't create any noise as such. Okay, scaling factor, yes, each 360 degree is divided, full step angle, full step is 200 poles is there, poles are there. Okay, each of them is further divided into 64 small microfolds. Okay, so total number of microfolds which are there is 200 into 64 times. So pole to pole is 200 different poles for 360 degree. So yes, it can move almost at 0.028125 degrees per increment. Okay, so electrical isolation is there, IP certified, it is IP certified. So this has capability to handle EtherCAT communication using soft real time using TwinCAT3 interface on a standard PC, and EtherCAT Ethernet card of standard PC should have Ethernet card with 1 gigahertz frequency. That is prerequisite to use any TwinCAT interface. Okay, programming will again follow similar stuff. We'll use TwinCAT automation device specification, TwinCAT ADS library, and that will call import it in Python interface and access the motor runtime variables which are defined in twin cat configuration tool which is there, that is the driver for it. Okay, finally, and that is for configuration and declaring all the objects, their parameters. Okay, so we'll see by example now. Okay, so yes, this is the motor that I'll be controlling. You see it has resolution of 1.8 degree, pole to pole gap is 1.8 degree. Mind it, this is not precisely a bipolar stepper motor. It is a kind of, because it is having a dual property of variable reluctance motor as well as hybrid bipolar stepper motor, that is permanent magnet motor. Okay, so in this case your winding is not straightforward. It varies like this. So you have north pole which is at the fore side of your armature, rotating armature, and aft side you have south pole, and there is more number of poles which are generated. So this is soft iron core which is capped from the top, from the front and the end, and finally it is a soft iron core and a permanent magnet. So it has dual. These are advanced architecture motors. When you see, you have less number of armature poles as compared to number of poles which are from all around. Okay, that is the stator poles. Okay, so yes, it can move at very small angles. So that is the reason it is able to move at 1.8 degree. But doesn't matter, even this motor follows the principle of bipolar stepper motor. It has 4 wires, and same way you have to shift your poles, right? So nothing to worry. Same drivers are suitable for this as well. So yes, a maximum number of steps per second is, this is very important parameter because of the rotor moment of inertia. It is static in nature. So once you start, you cannot go to next position immediately. So that basically limits the number of steps per second. That is, you change in pulses. You cannot move at very high speed because it has its own, rotor has its own moment of inertia. It cannot quickly pick up and reach. So if you go beyond that, it will start slipping. That means your poles will move, but your rotor will not move. Okay, it won't be able to follow that. So electrical isolation, 500 volt axial load. This also is very important because most of the time stepper motors are used to pull and push some sort of pinion drives. Okay, so screw and pinion drive where it can pull a bed, maybe a tool sometimes. Okay, so axial load more than this is not acceptable. Any stepper motor or normally servo motors also, they are specified, sizes are specified like this. So it is NEMA 23, that is National Electrical Manufacturers Association. NEMA 23 means 2.3 inches, that is approximately 56 millimeter. Okay, 58, but if it says N2, it is 56 millimeter. Okay, protection class is IP 54. You see, this is all industrial specifications. Things are same. Okay, so different microfolds are possible. So increasing the microfold will ultimately reduce the maximum speed possible. You see, so maximum speed. So is bigger are the steps, higher is the speed. That is quite obvious. So that works with this also. So this is the circuitry which is there. I have rigged up. It is very similar to the way we rigged up for DC motor. So you see, this is power which is supplying 24 volt power. 120 watt is the maximum which it can supply. This is going to your EtherCAT coupler also, which is connected to industrial PC. The green one is the communication wire, whereas the red one is power wire. Okay, so power is drawn from the UPS. UPS takes power from this power supply SMPS, and finally from the UPS it goes to your different devices. Okay, and in between you also have EL9550, which is nothing but a filter, noise filter. That is, again it is here, and from filter it goes to the driver. It goes to the motor driver EL7031, the one which you saw here, EL7031. Okay, ultimately this card is there. This finally connects your stepper motor phase A, that is A1, A2, and phase B, B1, B2, 4 wires of stepper motor. Okay, so this is the setup which I have used. Okay, This is the physical setup that you can see. Forget about DC motor and BLDC here. So stepper motor is fitted here. These are all EtherCAT. This first one is the EtherCAT coupler, then you have filter, and then you have rest of the motor drivers. Okay, so this is your industrial PC. So on the top you have a HMI. So yes, now I'll communicate this to a regular PC, not using the HMI here. Okay, so same way you have to do configuration. You just open up a TwinCAT environment. When you can select your system which is connected to this through EtherCAT. So that is the IPC which was connected. IPC is further connected to different IO boxes and the motor drivers. Okay, so I have just selected my system. Okay, choose the target system. I have scanned for all the boxes. I selected it, right click, scan for the boxes. It has found out, yes, these are the components which are now fitted one after the other. If you look carefully, it has different IO boxes and it also has different motor drivers. So it has detected all of them. One of them, that is EL7031. EL7031 is for this one, terminal 4. EL7031 is your stepper motor driver. So this driver now has can be declared. It has an object which has all the variables. As you know, you can say it. I'll show you also. So you have to link this particular terminal and make it an access. You link this PLC object access to a physical environment. Okay, so now this linking is done to the physical environment. Now what this object allows you, it allows you to handle all these parameters. So this is the status, that is through the feedback. Okay, this is the status, that is through the feedback, and this is what can be controlled. So you see, you can control the torque, you can enable, you can do velocity control, right? And more so, you can give it a pulse, and it can move. Okay, so that is the input side of it you can give. Okay, so now directly going to the video demonstration of it. Okay, so now you see, I'll just restart this one. Okay, just watch carefully. So yes, so you see, initially it was at 0, 1.8 degree, then 3.6, then 5.4. So you see, it is moving in steps. It is moving in steps. 1.8 degree, 3.6 degree, 5.4 degree. So this is coded like this. If you can look carefully, if I press A, it goes by one full step, that is 1.8 degrees, with a predetermined velocity which is fed here. That is the velocity parameter which I have updated from here. So it starts like you have a PLC object which is created by creating a connection to the IP data, which is through which EtherCAT, through which it is connected, your device is connected. Okay, and that is the port. So you just create an object, open it, access is variables, and just set stepper motor status as 1, and you have also created this object, set this as enabled, it has made it 1. Okay, so finally every time you go, you have to set its velocity and set the angle, velocity and angle. So for A, it is defined as going with some velocity, you see it is here, and then I have just fed it with 1.8. So every time I press A, it moves. Okay, so you just watch. So it is 7.2, then 9, okay, and so on and so forth. So finally I made it go totally to 360 degrees. So for that to happen, I have defined W parameter. So if that happens, it will quickly go to 360 degree, one full revolution with the predefined velocity. So now I'll press W. So it goes directly from 0 to 360 degree with a particular velocity, 360 degree. From 360 degree, it will go back to 0. If I press another key sequence which is defined in this code, you look carefully. Okay, and then same sequence is repeated with a higher velocity. This time it is moving with a higher velocity. So this is how I have made it run. So yes, now you know very well how a stepper motor is. It can be made to run, different types of stepper motor, how they are internally connected and how they are constructed. So yes, not much in detail for micro stepping you have learnt, but yes, you at least got the philosophy here that yes, it is very much like a bipolar stepper motor, and you can gradually shift the pole using current chopper drive. That's all for this class. In the next class, we'll be discussing more about BL brushless DC motor. That's all. Thanks a lot.